Okay, so now that we learned how to determine the configuration of a chiral carbon in the last lecture video, let's talk a little more practical about the differences between these enantiomers, these mirror image isomers that have at least a chiral carbon, at least one, and that are non-superimposable on their mirror images. And the first question that comes to mind is, well, what are the physical property differences between a pair of enantiomers? And the answer is there's only one. Because enantiomers have the same melting point, boiling point, refractive index. If you put them on a TLC plate or a column chromatography, they would be the same spot. They would have exactly the same RF value. If you GC them, they give one peak. So the enantiomers are identical in all physical property except one, and that's how they interact with plane polarized light. So the question then becomes, well, what is plane polarized light? And light, or electromagnetic radiation, is made up of two components. It's called electromagnetic radiation because it's got an electric component and a magnetic component in its waves, and those are perpendicular or orthogonal to each other. And so electromagnetic radiation, such as light, can be manipulated with a polarizing lens. So in this demonstration, which you can watch, and we'll fast forward through this and you can watch it the full on your own, but he has two large polarizing lenses, and you might have polarizing lenses in your sunglasses. You might have them in a photography lens. They sell polarizing lenses to cut down on glare. That's why they're used in sunglasses. But let's let him show you the what happens with polarizing filters and how you can create plane polarized light and how you know that it is plane polarized light.
These are polarizing filters, and what they do is that they have a particular direction in this material. They're polymers that are lined up in a particular direction and only allow electric fields to pass through that are aligned in that direction. Electric fields that are perpendicular to that direction get absorbed by the filter.
Now I'm going to stop the tape here for a moment and just give you the classical definition here of sort of what a polarizing filter is. A polarizing filter is kind of like a picket fence where the light of only one orientation can pass through the slots. So that's what he was talking about when he said that the electric field vectors can only be a certain way.
And to demonstrate how this works, you can see already that it's a little bit dark. It looks like dark colored sunglasses. But it's more than just dark glass. It's if you put two polarizers together and their polarization directions are lined up, then most of the light passes through. Whereas if you rotate them 90 degrees, you can cut out almost all of the light. I think by now my face should have disappeared, which is not a bad thing. And then as we continue to rotate them, we're bringing the two transmission directions into alignment with each other again. And Polaroid, I believe, was the first company that produced polarized lenses. And if you have, you can find out if your lenses are polarized or not by taking one lens off and then turning it perpendicular to the other one, and if the image disappears, then you know they're polarized lenses. We can do the same thing by just taking these and and putting it in front of this other and then rotating. And I think you can see that at this point the image goes completely dark through that lens. Now we're back to being able to see through it again. And so these are polarized lenses. These are just dark lenses that are not polarized, and you'll see that the image does not depend on orientation. And so that's one way to tell. The polarized lenses are polarized in the vertical direction so that light that's reflected from the surface, glare, for example, on a rainy day, will get cut out by the vertical polarization. We'll talk more about that later. That's polarization.
Okay, so in that demonstration, what you saw was that if one lens allows the waves that are oriented up and down to go through, if you put a second filter behind it that was perpendicular, then no light came through. And we deal with polarized the light that goes through the one lens. So if I had one lens and I passed light through it, I would only get one orientation of light going through that lens, and that's what's called plane polarized light. We deal with plane polarized light all the time. As he said, if you go out and you look at light that's reflecting off of any object, it's polarized. The sun, the sky, the blue sky is polarized light. So if you do have a pair of polarized sunglasses, if you look up at the blue sky and you turn your head one way or the other, if the blue color changes its intensity and its color, you have polarized lenses. And it's used in photography to cut down the glare off of water or off of an object. And so that's what we use. So it was well known in the 1800s or so that you could make these polarized lenses, or better yet, there were certain materials that created plane polarized light. And so what we can do is, if we pass unpolarized light that has orientations of all of the electric and magnetic field vectors in all directions, when you pass them through a polarizing filter, only one comes out the other end, and that's what's called plane polarized light. So what happened was that Pasteur, the same guy that discovered milk, and I love telling that joke because the first time I did, when I taught in Kansas, when I left the lecture room was in a different building. So when I left the building, all the kids that were out smoking afterwards, boy, what a time that was. They all like stopped me and they're like, he really didn't invent milk. And I go, I know, it was a joke. But Pasteur, he knew about plane polarized light, and so what he did was he took crystals that were that grew on the underside of corks and wine bottles. It was called tartaric acid. And what they knew about tartaric acid was that it formed a particular shape crystal. Some of the crystals had a mirror plane through them, so they were asymmetrical, and they were not superimposable on their mirror image. And then there were other crystals that were mirror images of each other. So the legend is that Pasteur sat down, he painstakingly with tweezers separated the crystals that were superimposable on their mirror to the ones that were not, and he put them into the left-handed version, the right-handed version, and then he passed plane polarized light through them, and found out that when you had one of the enantiomers, it rotated plane polarized light by a certain number of degrees, either to the right or to the left. And so when you pass plane polarized light through a sample that contains a chiral molecule, it will rotate plane polarized light by some number of degrees that we'll call alpha. So there's another demonstration here to show you that sugars including the Karo syrup, those are all molecules that are not superimposable on their mirror image. They're all chiral molecules. And so you can watch these two videos where it will show you how we could determine that by using the plane polarized lights. And you can go ahead and watch those at your leisure. One uses a laser, actually, which is kind of a cool demonstration. But we are not going to watch them right at this moment. You can watch them. So what happened was that when Pasteur did this, he found that one form of the crystals, one-handed form of the crystals, rotated plane polarized light to the right, and one rotated to the left. And so those are called dextrorotary and levorotary. So if it rotates plane polarized light clockwise, if it rotates it clockwise, that's clockwise, then it is considered dextrorotary. If it rotates it counterclockwise, it's levorotary. So this is D and this is L. The degrees of alpha would be positive in this case. The degrees of alpha would be negative in that case. So then what Pasteur did was he made solutions of those, and he found out that when the solutions had the same concentration, they rotated the light in opposite directions but the same number of degrees. And then when he mixed those two together 50-50, he found out that he had no rotation of plane polarized light. So now we call the dextrorotary the D, and we call the levorotary the L. And the only way to determine if an enantiomer is D or L is to put it in an instrument called a polarimeter and measure its degree of rotation and determine whether it's positive, clockwise D, negative, counterclockwise L. And so you have D and you have L. Sugars, naturally occurring sugars, all are D. Amino acids are L. Now, there is no direct correlation between R and S and D and L. Some R compounds, some R chiral centers are D, some R compounds are L. So there's no direct correlation. You have to determine the D or L by experiment. Okay? But this D and L term is used for determining like sugars are D and the amino acids are L. So that's where the difference between configurations and optical rotation is. The configuration is the exact three-dimensional structure around a chiral carbon. Optical rotation is whether the molecule rotates plane polarized light D or L. And there's no direct relationship between R and S and D and L. Some R's are D, some R's are L. Okay? And if you have a molecule with more than one chiral center, which we haven't done yet, but we will, then it doesn't really fit this, but the overall molecule is either D or L. So what Pasteur found was, and one of the crystals that you found on the cork of the wine was called racemic acid, and so it had a mirror plane of symmetry in the crystal, and it basically didn't rotate plane polarized light at all. So what has become known as a racemic mixture is when you make a 50-50 mixture of enantiomers, because one enantiomer rotates to the right, one rotates to the left, and they cancel each other out, so you get no rotation. That 50-50 mixture is what's called a racemic mixture. So the issue becomes that if I have a molecule, such as maybe a chiral drug, the molecule itself, how do I tell someone what the exact number of degrees that they should get for that molecule is? And that exact number of molecule or number of degrees might very easily be used to determine the purity of a chiral molecule, and maybe it's a chiral drug, and I'll talk about that in a minute. And there's also a reflection piece that you're going to do on looking at the chiral drug thalidomide. So how do you know what number of degrees? Could this be used as a physical property for a chiral molecule? And the answer is yes, but the number of degrees is dependent on a number of things. First of all, it's dependent on the compound that's being used. Well, if I'm going to use it as a physical property, I want that. It's dependent on the length of the sample cell. The longer the cell, the bigger the rotation. It's also dependent on the concentration of the sample. The more concentrated, the more rotation. Both of those make sense. And it also depends a little bit on the solvent, although not tremendously. So when you change the cell length and you make the cell length longer, you have polarized light interacting with twice as many molecules. And so, therefore, it rotates twice as much. Right? When you change the concentration and double the concentration, twice as many molecules, twice as much rotation. So if I'm going to tell someone that I measured my drug molecule and it has this many degrees of rotation, I need to normalize this. And the normalization is what's called the specific rotation. So the specific rotation is alpha in brackets with a D. The D is a specific wavelength of a sodium vapor lamp that's used, and 20 is the temperature. So this is the specific measurement measured, a specific rotation measured at 20 degrees using the D line of sodium. So what that is dependent upon is this. Our experimental rotation, measured in degrees from the instrument, times the cell length. And the cell length is measured in decimeters, where 1 decimeter is 10 centimeters. Now, organic chemists are horrible. You know, we avoid math like the plague. So, shouldn't be saying that in the COVID thing, but we really do avoid math. So, most cells are a decimeter long. So that way, this is 1. And concentration, I don't sometimes know the molecule that I'm looking at. So this is normally measured in grams per mil. Because I can measure out grams per mil. I don't need to know what the molecule is to make a solution of that concentration. And so what this does is this normalizes the experimental rotation into a physical property called the specific rotation. So if I measure my concentration, my cell length, and I measure the observed rotation, and this will either be plus or minus, depending on whether it's D or L, then the specific rotation gives me now a physical property that I can use to measure the purity of the molecule up to a certain point. Okay, so here is an experiment that we will be doing in the lab course, and there are many chiral drugs out there that you purchase that are one enantiomer over another. And the reason for that is that the molecules that are in one enantiomeric form will react differently than the molecule in the other enantiomeric form. And I'll come back to that in a couple of minutes. But this is naproxen sodium. This COO-NA group is a deprotonated carboxylic acid with a sodium counterion. So naproxen sodium is what's in an Aleve tablet, whether it's generic or whether it's a true brand Aleve tablet. And the idea of making the Aleve tablet in one enantiomeric form is that the negative, the L form of the Aleve, of the naproxen sodium, will take care of my headache. The D form has a tad bit of liver toxicity. And so the drug company has to make sure that they only sell us the L form and not the D form. So how do you determine the purity of a molecule? Well, the book gets into more details of this, but basically what I can do is I can measure the specific rotation of that drug molecule. And in this case, the literature values from about minus 15.3 up to minus 17, depending on what value you look at. It really should just be one or the other. But what happens is that if I have a mixture of enantiomers, then what happens is they counteract each other. So, for instance, what is called the enantiomeric excess, which is the percentage of the major enantiomer over the percentage minus the percentage of the minor enantiomer, is what's called the enantiomeric excess. How much in excess one enantiomer is over the other. So, for example, if you had a 75-25 mixture of two enantiomers with the plus enantiomer, the D enantiomer being 75%, and the L being 25%, what would happen is the 25% L would counteract 25% of the D, so that we would end up with what we call 50% enantiomeric excess. Now, for this specific rotation, that means that a 50% enantiomeric excess would be 50%, my rotation would be 50% of, let's say, minus 17 degrees. And so that would be the observed, that would be my specific rotation that I measure would be basically minus 8.5 degrees instead of minus 17. So you can get your percentage enantiomeric excess by dividing your observed specific rotation of your mixture over the specific rotation of the pure enantiomer, where the sign of the observed mixture, the sign of the mixture usually is the same as the sign of the pure. So that times 100 gives you the percentage enantiomeric excess. Okay, so that's actually where the optical rotation comes into play. So if I had a literature value of minus 16 for naproxen sodium, what I would say is that my percent enantiomeric excess would be minus 12 over minus 16, which is going to be 3 over 4, which is going to be 75%. Times 100 would give me 75% enantiomeric excess. And so what does that mean? That means that the two numbers, the percentage of, in this case, the major enantiomer, which is L, minus the percentage of the D enantiomer, must equal 75%. But the percentage of L plus the percentage of D must equal 100%. So I have two equations and two unknowns, which I can go ahead and solve. We could do all sorts of methods here. We could use linear algebra and solve it by the matrix method. Why don't we just add them together? 2 times the percentage of L equals 175%. So the percentage of 175 over 2 is 87.5%. The percentage of D then is equal to 100 minus 87, which is 12.5%. So we can calculate the percent D and L from the specific rotation of a mixture. The problem with this is there's a certain limitation of how high the percent can be before you have no sensitivity in this measurement. So if I'm going to measure the specific rotation or the purity of a drug, and I need to know that to 99.99%, optical rotation isn't going to work. But that's how we'll do it in the lab. And that's how we determine the purity or the percentage of a mixture of enantiomers. Okay, so what are the differences then in chemical properties of enantiomers? The differences in the chemical properties are that enantiomers react the same with other non-chiral molecules. but they can react differently with other chiral molecules. My example of this is that if you've been in the lab and you've seen, the lab gloves, that's like a Muppet lab glove. In our lab, there is no box of left and right-handed gloves. Why? Because the glove has a mirror plane of symmetry that cuts right through the center of the glove if I held it on edge. So my left and right hand fit perfectly inside of that glove. That glove is achiral. But what about a golf glove or a winter glove or shoes? Well, if I try and put the right-handed glove on the left hand, it's going to be different than on my right hand, because in that case the thumb comes out and it doesn't have that mirror plane of symmetry. So my left hand reacts differently with my gloves than my right hand, or with my gloves, with my winter gloves versus the lab gloves, because one is chiral and one's not. So with drugs, what that means is that if you have a chiral drug like naproxen, sodium, other molecules in your body are chiral. Proteins are chiral. Enzymes are chiral. DNA is chiral. So those other chiral molecules, that drug can react differently with and the two enantiomers react differently. So that leaves, that's a big issue. You'll watch a video and do a reflection piece on the drug thalidomide, which was given to, not in the US, but in a lot of other countries, thalidomide was given as a sedative to pregnant women. And what happened was one of the enantiomers was a sedative, the other one caused birth defects. And you'll watch the video about the woman who worked for the FDA that actually kept making the drug company go back and do more studies, and it's why thalidomide was never actually sold in the U.S. during the 60s, because that was her area of research, was basically phytotoxins, and so she actually stopped the drug from ever being sold in the U.S., but in other parts of the world it had horrible effects. So you'll read about that, and in your reflection piece talk a little bit about that, what your impressions are. Another example would be sugars. So sugars are the D form. If all the sugar in the world changed to L, we couldn't metabolize it. And there's a good essay question that's out there about Alice and the looking glass, so that if Alice actually walked through the looking glass, what biochemical processes of hers would remain the same and which ones wouldn't, because when she walks through the looking glass, she changes the chirality of all of her enzymes and proteins. An interesting question. So the chemical property is different when it's reacting with another chiral molecule. I'll show you an example of that in a moment. The physical properties, as we said, the only physical property that's different is how they rotate plane polarized light, which is useful but not that useful because everything else is the same. So that's a bit of a problem. So let's talk a little bit about Fisher projections, another way to orient chiral centers, and then we'll go back and finish up with looking at more about the physical properties. So what is a Fisher projection? A Fisher projection is just another way of looking at the tetrahedral representation. So in this molecule, your tetrahedral representation would look like this. Okay, there's the red, there's the blue, there's the green, and there's the white. So in a Fisher projection, what we do is we orient the molecule this way. So that basically what we have is we have two groups pointing towards you and two groups pointing away from you. And the Fisher projection is written like this. And it's understood that the horizontal positions are bold and the vertical positions are dashed. And if you forget that, it's the bow tie model. So that's what a Fisher projection looks like. So we haven't had a quiz question yet. We probably should. So here's my question. My question is, in this Fisher projection, is this chiral center R or S? Now here's the thing. In the Fisher projection, since you have two positions on dashed wedges, it does not matter where you put the fourth priority group. It can go on either the top dashed wedge or the bottom dashed wedge. And so, is this R or S? So the video is gonna stop, and then it'll ask you, is this R or S? And then you can figure out your answer and then answer that question, and then we'll come back and figure out whether you were right or not. Okay, are you back? So is this R or S? Well, priorities. Priority group number: oxygen, carbon, hydrogen, carbon. Who's number 1? Oxygen. Who's number 4? Always hydrogen. Carbon versus carbon. What's attached to this carbon? 3 H's. What's attached to this carbon? More than 3 H's. Actually 2 O's and an H. Who wins? Number 2, number 3. So in this molecule then, here are my numbers. 3, 4, 1, and 2. Now Fisher projections, the book will tell you what not to do with Fisher projections. If you're one of those people who doesn't like to hear what not to do because then you do it, don't read that part of the book. And I'm not going to go there. Fisher projections, the easiest thing to do is just group switch. I can switch 4 and 3 or 4 and 2, it doesn't matter. Let me switch 4 and 3. One switch, switch 1 and 2. 2 switches, so now whatever I determine is the original configuration. So going from 1 to 2 to 3 is clockwise because 4 is pointing away from me. Yay, I finally have an R in one of these problems. So this one is R. Okay, so that's how we handle Fisher projections. And just remember, it's a bow tie structure. And my suggestion is always to group switch with Fisher projections. We'll come back to a little bit about that in the next lecture. Okay, so in terms of the configurations here, we have this molecule, and this molecule has now 2 chiral centers. So the next thing we want to talk about is, let's draw out the mirror image of this molecule. It has 2 chiral centers here. So let me come over here and draw in a Fisher projection like this. Let me go ahead and draw its mirror image. Now, what's the relationship between these 2 molecules? If you said that they are non-superimposable mirror images, you are correct. Because you can't superimpose the right into the left. You might say, but what if I just take this molecule and I just basically flip-flop it so that the O matches up with the O, the CH3 matches up with the CH3? If you do that, remember, these are bold. These are bold wedges. And these are bold wedges. So if you try and just take this molecule and flop it over, the OH will match up with the OH, but it'll now be, if it flops over, if you rotate this around 180 degrees, the oxygen's now on a dashed wedge and it doesn't match up. So these 2 are non-superimposable mirror images, which means that these are enantiomers. Now, the question would be, what's the top carbon? Is it R or is it S? And let's do these first two, and then I'll ask the other. We'll draw two more molecules, and I'll ask you what to do there. So in this case, we know oxygen's number 1. We know hydrogen's number 4. I've got a carbon with 3 hydrogens versus a carbon with more than 3 hydrogens. That means down here, this one is number 2, and this one is number 3. Now, what I like to do in determining R and S off the Fisher projection with more than one chiral center is I'll draw it up here with the bold and dashed wedges. And I'll put my numbers in. 1, 4, 3, and 2. So I kind of separate this and I move it up here. I would do the same thing down here. Hydrogen, 4. Chlorine, 1. C with 3 H's, 3. C with more than 3 H's, 2. And so if I can put it in a tetrahedron or a Fisher projection, I can now determine R and S. Fortunately, I drew this molecule so that 4 is automatically behind me in both cases. So going from 1 to 2 to 3 isn't counterclockwise, which means the top is S. Going from 1 to 2 to 3 is clockwise in the bottom case, and so it's R. So the top carbon attached to O is S, the bottom carbon attached to chlorine is R. What is the combination here of R and S for these two chiral centers? So the question is, what is the top and then the bottom chiral centers in this enantiomer? Okay, so we'll stop the video and then you can go ahead and tell me. You'll have basically 4 choices. You'll have RR, RS, SR, SS. So top first, bottom second. What is the configuration of those two chiral centers in that molecule? Okay, are you back? Well, since this chiral center is a mirror image of this one, its configuration is exactly opposite. So the top would be R and the bottom would be S. That was easy enough. So whenever you have enantiomers, every single chiral carbon is going to have exactly the opposite configuration. Okay? So that's the answer to that question. Now, let me erase this because I need space to do the final step here. Okay, so now let's change this molecule, because one thing that I didn't say earlier was this, that the number of stereoisomers for a molecule is equal to 2 to the n, where n is equal to the number of chiral carbons. So when we've been doing these problems with just a single chiral carbon, there have just been 2 possible stereoisomers. But now with 2 chiral centers, that means there's 2 squared or 4 possible stereoisomers. So what I just started with a molecule and I wrote its mirror image. But can I write another molecule that's not the mirror image? And the answer is yeah. Let's take the top carbon and keep it the same, have the same orientation as, let's call this molecule A and call this molecule B. So let's have the top carbon be the same as in A, but let's have the bottom carbon be the same as it was in B. So what's the top carbon's configuration? Well, it's going to be S because it's what the configuration was over here. What's the bottom carbon's configuration? It was S because in this case this was R and this was S in the enantiomer. So notice I went from SR and RS being enantiomers, and now I made the SS. And it has a mirror image that is not superimposable. So let's draw the mirror image of this molecule. And so what would its configurations be? Well, it would be R and R, because now these two are non-superimposable mirror image isomers. They are enantiomers. So now I have the enantiomers, two pairs of enantiomers. So and I'll call these, just for the sake of argument, I'll call those C and D. So now the question is, what's the relationship between A and C, or A and D, or B and C, and B and D? Because A and B are enantiomers, C and D are enantiomers, but what's the relationship between any other pair? And these are what are called diastereomers. So diastereomers are non-superimposable, non-mirror image isomers, which is a great definition, but it doesn't tell me a lot. They must have at least 2 chiral carbons, and at least one chiral carbon has the same configuration in both, and at least one chiral carbon has the opposite configuration in both. And that's the case here. What's the relationship between B and C? B and C are diastereomers, because R, S, S, S. At least one same, at least one opposite. And so therefore we have our enantiomers, or our diastereomers. So in a set of 4 molecules, there are always 2 pairs of enantiomers, but most of the relationships are diastereomers. And so basically, if you think about this, how did I get this number 4? Well, each one of the chiral centers has the possibility of being R and S. So if I have 2 chiral centers that each could be R and S, I could have RS, or SR, or RR, or SS. That gives me my 4 combinations, and that leads to 4 different stereoisomers. Okay? So the next question that we're going to have is, well, okay, what about these physical property differences and chemical differences, or reactivity differences for diastereomers? But before we get to that, let's just go ahead and stop this lecture for today. And there is an online quiz where I'm going to give you a molecule to start with, sort of like A, and I'm going to ask you to draw the other 3. But in this case, 2 of those are going to be superimposable on each other. And so once you do that assignment, then what we'll do is then we'll talk about what happens if you have a pair of molecules that does have chiral centers, but they are superimposable on themselves. That has to have a new name. And so that's what we will do in the next lecture.